Hi there, welcome back to the channel and welcome to the next installment in the Back to Basics series in the restoration of this tube radio. And this time I want to complete the AM section so that we can actually turn this into an actual radio. And just a spoiler alert, we get that done with a bit of a hiccup in between. Oh, and by the way, that noisy thing in the background is my new 3D printer, which I'll be talking about shortly. In this video, I want to go into quite a bit of detail on the AM. We'll check the AM. We'll find out what's working, what's not working, how to detect whether something is working. More specifically, for example, the oscillator, which we had a problem with here. So if you enjoy this sort of thing, stick around and enjoy the video. Well, folks, we know we've got an amplifier that's working. We've got a little tube amp, single-ended, and it's working. But do we have a radio? That's what I'm going to find out right now before I look at anything else. So the first thing to do is put in the missing tubes. And those two tubes are the IF amplifier, the F89. Now I've already cleaned these pins and the sockets, so we can put that tube in, and we've got the ECH81. I'll go into what they do later. I want to see if we've got radio reception at all. I have the antenna connected at the back. The antenna that I'm using is obviously the AM, and I'm getting the antenna signal from the mini whip, which I've got to put on. The mini whip's under renovation, as you can see. My speaker is connected. It's on speaker. I have the radio connected to the dim bulb tester. That is sitting over there, all ready to go. I'm going to put one light bulb only. I'm not sure what those tubes are like, so I'm not going to risk it. We'll try it on medium wave. Put the volume highest on max. And now all I need to do is switch on. So far so good. We've got that thing lighting up. It's gone down. The tubes will be starting to draw some current soon, so that should light up a little bit more. Remember, one light bulb is 40 watts, so it's very, very restricted. Am I getting anything? The light is sort of coming on. Yep, it's glowing. I hear a crackle. I'm going to give it one more light bulb. I can hear a crackle. Can you hear that? It's not much, is it? Let's try tuning. Just some noise. Long wave. Ooh. Ah, you're getting long wave. Shortwave? I've got something making a real big noise in here. Well, that's certainly receiving. This is without changing any capacitors on there with the original tubes. When I say I haven't changed any capacitors, obviously the AM section, the amplifier and preamp you've seen. So what have we got here? We've got long waves working, medium wave is not. I wonder if the oscillator is working at all. Let me just tell you what it is that is working at the moment, and then we'll figure out what it is. I know where the problem is not. Okay, from the fact that long wave is working and short wave is working, medium wave is not. FM I'm not even trying now, the tube isn't even in, we'll leave that for later. But because these two are working and that one is not, there's a big section of this radio that I know is working perfectly well. It can be aligned, it can be corrected, improved, but it's working. Let me show you what that is. This is going to be the quickest explanation of how a heterodyne receiver works that you're probably going to see. I'll put a link below which is actually a Wikipedia link to Superheterodyne Receiver, and I really recommend you read that. It's very, very good. But let's get to my simplistic explanation. What we have here, a radio, basically, is we want to take the signal coming in at the antenna, and we want to send it out of the speaker, right? Now, we've done quite a bit on this flowchart already. We have the audio amp, which we know is working. So we know that part from there forward is fine. What else do we know? We know that this thing is demodulating AM because we have been able to pick up shortwave and long wave. And that's the AM demodulation in effect, which means our demodulator is working. But there's also a few other stages that we know are working, including the IF, the second IF transformer or filter, the IF amplifier, and the first IF filter. In other words, we know that everything from here forward seems to be working. And the reason we know this is working is because we can hear AM, any AM. If we only picked up long wave, we would know this is all working. And the reason for that is that from this point forward, this thing works on one particular frequency, which is the IF frequency, which is the intermediate frequency, which happens to be 460 kilohertz in this case. Now, how does that arrive at that figure? Well, we have a mixer. And the mixer, what the mixer does is it takes our signal from the antenna, from the front end, it mixes it with a local oscillator frequency, and it produces the IF frequency over here with a whole lot of other frequencies, but it produces the IF frequency that contains the radio information. So if you're listening to a talk radio, it'll have 460 kilohertz carrier with the audio superimposed on it, amplitude modulated on it, okay? Now, how is that produced? Well, we have our RF front end, which is tuned. So let's take an example where we want to listen to medium wave or broadcast band, 1 megahertz, 1000 kilohertz. When we tune the tuning condenser, we tune to 1000 kilohertz. We see it on the dial, and we know we're supposed to be tuning to that station, correct? Well, we're not getting anything on medium wave, but let's take, for example, the long wave. If we tune to a station at, I happen to know the BBC Radio 4 is 198 kilohertz. So we tune on the dial, we see on the dial 198 kilohertz, we tune it to that, and 198 kilohertz should be coming through here. Now we want 450 kilohertz over here. So there's a mixing that happens, and it's created, or it's achieved, by having a local oscillator over here that produces a frequency which is related to that front end frequency. So when you tune there to, let's go back to the broadcast band because it's easier to work with those figures. Let's say you're trying to listen to a station at 1000 kilohertz. This one will tune to 1460 kilohertz. In other words, the IF frequency above that. And the reason these tune together is because the tuning condenser has two sections. The front end tunes to the 1000 kilohertz, and the way the coils and the capacitors, in other words, the tune circuit is set up in the local oscillator, it'll mean that when you turn that condenser, the tuning condenser, it'll tune the other section of the tuning condenser here as well, and it'll ensure that this one produces 1460 kilohertz. So we create what effectively is the FO, the oscillator frequency, and we have the input frequency, and what we get out of the mixer is a series of frequencies like that. We get the difference, and we get the sum, and we get the original frequencies. So let's just slow down for a second. Once this signal, which has been tuned to the 1 megahertz that we want to listen to, okay, and this signal, which has been tuned because of the tuning condenser lineup or ganging, see this dotted line? This one has been tuned to 1460 kilohertz. This mixing action, this heterodyning, produces multiple frequencies, including FI. So at this point, we should see 1 megahertz. We should see FO, 1460 kilohertz, 1.46 megahertz. We should see the sum of them, FO plus FI, so 2.46 megahertz, and we should see the difference as well. See that? So we should see 1460 kilohertz minus 1000 kilohertz, 460 kilohertz. Now, what happens if we're listening to something at, let's call it 10 megahertz? Well, the same thing applies. If we want to listen to something at 10 megahertz, our local oscillator will tune to 10 for 60, which means that the difference will be for 60 kilohertz, and the sum will be 20 for 60 kilohertz. We get something like this. In fact, we get exactly this. We have Fi, the input frequency, we're tuning to 10 megahertz. On the dial, we tune it. At the same time as you're tuning to 10 megahertz, the oscillator is getting tuned to 10,460 kilohertz, which means our difference is 460 kilohertz, which is appearing here as well, and the sum, which we're not interested in. Now, what happens if we're tuning to, let's say, 198 kilohertz? Then we're left with something like this. The tuned frequency at the front end that we want to listen to is 198 kilohertz. The local oscillator gets simultaneously tuned to 658 kilohertz. The difference is, again, that one minus that one is 460. And the sum is 856, which we're not interested in. So what you can see here is regardless of which band we're listening to here, regardless of which frequency we tune to, and I'm talking about the 3 AM bands, long wave, medium wave, and short wave. Okay, that's what we're talking about here. Whatever band we're in, whatever frequency we tune to, it automatically forces the difference of 460 to appear through the mixer. And that is the only one that we tune to go through. We have the first IF transformer that we tune to 460 kilohertz to allow the signal to go through. Now, by tuning it, we're allowing the 460 to go through, but we're cutting off the others. We're cutting off 198, we're cutting off 658, and we're certainly cutting off 856. So 460 is getting through to here. It then gets amplified through this IF amp, which happens to be the EF89 tube we've got, and it gets here. And we have another filtering stage, which creates another sharpening of that filtering of 460, which contains the information we want to listen to, right? The audio. So it's modulated with that audio. That carrier gets through, it goes through a demodulation, produces an audio signal, and it comes through the amp, out of the speakers. Okay. Now what we know is that there's a lot of stuff here that's actually working. In fact, we know that everything from here after this, in fact, the mix is working as well. We know that this is all working. Isn't that great? Now, why are we not getting anything on medium wave? Well, we know that the front end is working for shortwave and long wave. We know that the oscillator is working for shortwave and long wave. And for some reason, we're getting just a hiss on medium wave. Now, the fact that we're getting a hiss tells us that something's coming through here. Something's coming through here. In fact, what's probably coming through here is my 1 megahertz, if I'm tuning to it, but it hits this thing, it comes through as 1 megahertz, it meets the 460 kilohertz filter and says, whoa, I can't go there. All right? So you'll just hear a hiss. Because I believe this thing, this part here, is not producing anything on our radio when it's set to medium wave. Now, how can we see that? How can we check that? It's very, very simple. I'm going to show you on the scope. Let's just show you the schematic quickly, and we'll talk about what it is we're looking at here. If you remember, we did this whole painting job where we identified different sections. Now, there are a few sections here that aren't of interest to us. We've got the power supply, which we know is working. That is all working. The audio sections, the audio preamp. We now know that the intermediate frequency is working as well. We know that the mixer is working, but we have a section down here. This thing is FM. We're not interested in it right now. This section down here, this is the link up with the local oscillator. This is the front end. Okay, there's the antenna, front end. And you can see that depending on which buttons you push, whether you push long wave, medium wave, or short wave, different coils, different capacitors get brought in. And this allows the tuning of this stage to match the section of the AM band that you want to listen to. And then, of course, you've got this capacitor here, that capacitor there. Those are the two ganged ones that do the fine tuning within the band, okay? Now, I believe this is working. I believe our problem is somewhere here. All right, how do we check that? Well, we can actually look for the local oscillator frequency it should be sort of a sine wave, and I'm going to show you how easy it is to detect that. Then we'll come back to the schematic and do some tracing and find out if my guess is correct and we do not have local oscillator on medium wave, then we can come back and do some troubleshooting and find out what's wrong with it. Got the radio on its back, looking at the underside, and this is the switching section. This over here is the switching section from the underside, and on top here you can see the switches, okay? There's AUS, there's the pickup, TA, that would be long wave, medium wave, and short wave. There's our FM, okay? At the moment I've got it on short wave, and if we follow this line down here, you see these coils and trimming condensers over here. These are coils, that's a trimming condenser, capacitor. There's another set of coils, 2 coils, trimming condenser. There's a trimming condenser, there's another coil. This lot here is under the long wave. This lot is under the medium wave. This lot is under the short wave. Now, if we look at the actual front end of the radio over here, I have isolated the front end that relates to the AM section. This here is the local oscillator for the 3 bands, with the switching that allows the specific band to be pulled in. This is the front end itself of, again, the 3 bands. This is the ECH81, which does the dual job here. One part of it actually acts as the oscillating element, driving the oscillator. You can see that this line over here goes to, or from the oscillator to the triode. And this side here is a mixer, which is actually receiving the signal from the front end as well. Now, if you look at this, it's actually quite simplified, but you can still simplify it further, because if you look at the shortwave, for example, you need the switch box, the switch schematic, to explain to you exactly what's happening here. These are the buttons, AUS, TA, long wave, medium wave, short wave, and FM. These letters correspond to different columns within that switch, and you can see here you go from, this is part of the FM, but this goes from A, B, C, D, E, F, G, H, all the way to M. And this is row 1, row 2, row 3, row 4. So if you talk about switch I2, you go to column I, you go up to row 2, it's that switch over there, that contact over there. You get the idea, right? So this is drawn in the rest position. Now the reason we say rest position is because this actually has an off switch, an AUS switch, which breaks all the contacts. It basically snaps everything back into the rest position. In some radios, you can push the off switch and it doesn't actually disconnect whichever band you've selected. It can be on, say, FM. You push it off, it stays on FM. So if you push it on, it stays back, it comes back on FM. This particular one, when you hit TA, when you hit AUS, it snaps everything back. So it's easy to draw them as unactivated. That's important to remember, okay? So if we follow the switch logic here, because these switches are labeled, there's K7, K8, K9. We know that K, for example, is this one here. It's one of the shortwave ones. The shortwave's got I and K, medium wave's got G and H, long wave's got E and F. So wherever you see I and K, you know that that is changed over when you push shortwave. Now, if I do a little bit of an exercise for shortwave and I follow the signal from the front end, this is what I get. There's my signal coming in here. It goes into there. That switch is now closed. Remember, that's I, which is on shortwave. So the signal goes through there, gets into that that coil sort of transformer there, comes out the other side. It's tuned. And the reason I know it's tuned is there's a trimmer capacitor there, but there's the main capacitor that is selected through this switch down here. That's one gang of the main tuning condenser. That gets tuned, and the resulting signal goes up into the mixer itself, the front end of the mixer of the ECH81 tube. Now, if we look at the oscillator section, I'm going to switch off the front end and do the same for the local oscillator section. It's something like this. Same logic. That switch is made. That one's unaffected. That's actually an FM switch. That's made. That's made. And you can see where the elements are that relate to shortwave local oscillator. And we know that if we have shortwave selected, this is what's working. And what's happening here is this condenser here, C13 and C13, are two halves of the tuning condenser, which you are turning to tune to the station that you want coming in at your antenna. And at the same time, it's tuning the frequency that your local oscillator is producing, which is higher than the front one by 460 kilohertz. And this is what's happening over here. You can follow it very, very easily. It's very, very logical. Now, what you see here is a series of tunable elements. What do I mean by that? Well, you know what a capacitor looks like. That's a capacitor. That's a capacitor. That's a capacitor. What does a capacitive trimmer look like? One of those that you can adjust. Well, here's one. See that? That's a trimmer. Here's another one. This one with the arrow through is a variable capacitor. It's the one that you're going to turn. The ones that you preset or adjust are the ones with the flat line over there, okay? Like T across. That's trimmable. And there's one. There's one. Where's another one? I believe there's another one. I saw 3 on the board. There's another one, right? These are the trimmable elements, trimmer capacitors, okay? Now you've also got trimmable coils. Here's one. See, that's a coil, but it's trimmable. You can trim it. You can adjust it. There's that adjustable handle through it, right? There's one. This one actually is adjustable in terms of the interaction between the primary and the secondary. This one's the same story. You can adjust it between primary and secondary. There's some more. There's some more. There's another one there. There's another one there. There's another one there. So these trimmers, these adjustable elements, these tunable coils, and the trimmer capacitors are those components that you're seeing on the underside. Now I've switched on the radio. I've got it on shortwave. Now we're going to look at this section over here, and what I'm trying to look for is I want to see the local oscillator signal if it's possible. And to do that, we're going to design a very, very special piece of equipment. We need some solid core wire. I've got a piece here which is about 1 foot, 30 centimeters or so, okay? I'm going to use this tube just as a former, and I'm going to wind a coil around it, and it doesn't really matter how precise it is or isn't. I'm just going to do this, okay? And just to keep it stiff and together, I'm going to do that. See how precise this is? Real high tech. Okay, what we've got now is a little coil of wire, okay? Very simple. Now you take your oscilloscope and you connect this across the scope. I'm connecting the ground to the one lead. I'm connecting the probe to the other lead, okay? Simple as that. Now this is insulated, so it's not going to short anything. And now if I look at the scope, if I move this towards this section here, and I start looking at, remember I've got shortwave selected, so I'm looking for the shortwave section down here. Look what I'm seeing on the scope. In fact, this is where it's really strong. See that? Whoa. Okay. I've hit pay dirt. I'm going to leave that there. Just the scope so we can see it. What do we have here? Let's see if I can leave this more or less stable on here. I don't want to touch anything. I don't want to disrupt anything. I just want to be able to leave it there like that. And now I can play with the tuning. See that there? The frequency we're getting here says 6.33 megahertz. Now that is in the shortwave band to me. Now, don't worry about this. I'm just touching basically the ground, so it does affect it. Now, if I tune this, I don't know if you can see what's happening with the frequency, but it's certainly going up. Now it's at 7.3 megahertz. If I keep going, I'm up to 10 megahertz and climbing. Let me change the scope again. That is my local oscillator frequency. And as it gets really high, it starts sometimes coming down in amplitude. That's not important. I'm up to 18 megahertz. I think that's the top, 18.6 megahertz, which would tell me that the top range of the shortwave band will be something like, let's see, 18.63 minus 460, so 18.2 megahertz or 0.3 megahertz, whatever it is, right? Now, watch what happens when I select long wave. Oh dear. it's gone. Well, yeah, it's gone for two reasons. One, the scope is looking for a very high signal, very high frequency signal, and now long wave is way at the bottom of the scale, and I'm not in the right place anyway. Let's see where I am. See there? Oh, welcome back. What's happened here? Change the scope. Look at that. Would you look at that? That is 833 kilohertz at one end of the band. Now, if I go the other way, it starts dropping. It's down to 750. Keep going and I can get all the way to the other side to, where are we, 630 or so. And I think I'm nearly there. There I'm at, call it 600. Minus 460 is about 140 kilohertz. Close enough, okay? That is my long wave oscillator working on that coil over there. See that? That tells me the middle one must be the medium wave. So if I go looking for medium wave and I select medium wave, what did I see there? Ha ha ha. I think it's just come back. It's just come back. That is 970. That is medium wave. That is medium wave. That's on 1.2 megahertz local oscillator. Change the scope. Let's see, let's go to 1. It's about 2 megahertz, 1540. The local station is 1530. That's what we're listening to. Now, if I take that away, I have to retune it because I'm actually loading that coil, so I'm changing the effect here. See that? So it does affect it. Everything you do on a tune circuit can affect it, even putting something close. Now, you see what I'm talking about? Now, we have done absolutely nothing. I have done nothing. That medium wave's just come back, which tells me that it was a switching issue. That is what probably caused that to disappear. Yeah, see that? I'm playing with the switch. Now it's gone. So the switches need cleaning. Okay, we've got medium wave. I've just got to spray some contact cleaner on there. I've got to clean the switches thoroughly again. I've done one quick pass through with contact cleaner. I've got to do it again. And this is the first time I've got medium wave right here. I was actually going to show you that we weren't getting medium wave at all. And I was going to show you how we fault find, how we trace for the signal here, looking for broken coils. Sometimes you have some of these little wires that are torn off, or sometimes it's actually the Faraday antenna wires that are loose. Things like that. That's what I was looking for. That's what I wanted to show you. And as it happens, it's a lot simpler than that. But at least you know now you've got a sniffer. Just one other trick. You don't even need this. You don't even need this thing. I mean, look at this. I can take this away and I can just connect the probe tips together. And if I put this on, where did we have a very strong one? Let's see. On long wave. It's not as strong. Let's try short wave. You can, it's not as easy, but you can see it there. It's not easy to, there we go. That is 16 megahertz. You can actually pick it up with this. There we go, that's better. You can actually pick it up just with your scope probe touching at the end, shorted at the end. This is acting as a loop. It's picking up the signal over there. I prefer to use this because it means I can go close. Even if I touch it, I don't cause an issue because this is insulated. And what I do now with this, I chuck it in the parts bin. I'll make another one next time because I guarantee you I won't be able to find it. That's how you sniff for local oscillator signals. So what do we need to do? Well, we've got a few caps to change. Did I say a few? Well, I lied. It's actually only two. That one and that one. I checked the entire AM section of the schematic. I checked all the resistors. They're all fine. A lot of the resistors that had actually been checked. Remember when we did the power supply, we checked those resistors that ended up coming to the anodes of the power tubes. So on the B plus lines, so a lot of it's already been checked. I checked all the others. They all work out fine. The only two capacitors that were the paper type were these two. That's the AGC cap, and that one is, I don't know where that is, but I replaced those two, and so all the AM has been done. Oh, and if you're wondering what that noise is, it's actually my new 3D printer. I've just got it. I've set it up and I'm testing it, and this thing is bloody amazing. I'll be talking about this in the future, but right now I'm actually producing something that I need for my little next mini project. Let's get back to this. So what exactly is left? Well, in the AM section, I need to align the IF stages and the RF. Now we'll get to that in the next video, I think. But what it means is I need to align these filters. These are the IF transformers, intermediate frequency transformers. They have to be aligned so that they pass the 460 kilohertz IF frequency optimally through. There are various ways of doing that. I want to show you various options with a scope, without a scope, you know, with a multimeter, with your ears, whatever. I want to try various options and show you how you can get that done as well. Then there's also the RF alignment, which means that you align the dial so that when it's pointing at a certain frequency, that's the frequency you're tuning to. We'll get into that as well. So for now, that's where I'm going to leave you. And as you can see, there's still quite a lot of cleaning to do. I've been resisting it because I wanted to do it all at once and show you some of the tricks that I use. But this thing is really getting on my nerves. All this dust and grime doesn't go well with me. But anyway, onwards. So I hope you've enjoyed that, and I hope you've learned something. So if you enjoyed that, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Links are in the description below. Links to the other videos in the series are also in the description below. So thanks for watching. Bye for now, and most of all, stay safe.